Example 7, yeah, already. Woo-hoo. Using both long division and synthetic division, find all the zeros of that cubic polynomial given that x plus 1 is a factor of h of x. Okay, so cubic polynomial. If our goal is to get it down to at least a degree what? Just restating everything for the recording. 2, then to get from degree 3 to degree 2, I need how many roots? 1, okay? And unfortunately, I was not given a root. I was given a factor x plus 1. But of course, if you know a factor, you know a root. And if you know a root, you know a factor. And if you know a factor, you know a root. So if x plus 1 is a factor, what is the corresponding root? -1. Good. So that should be enough. Now, you can either long divide h of x divided by the factor x plus 1, or synthetically divide with the root. You always long divide with the factor, but you synthetically divide with the root of that factor. So let's skip the long division. And again, I won't tell if you won't tell. We'll just say we did it like in our head or on another piece of paper or something, and our parrot pooped on it or something. Okay, that's a little more creative than your dog ate it. No one ever believes that a dog eats paper, right? But a parrot pooping on it, that's believable. Now, how did it end up in the bird cage to begin with? I put it there. Okay. Help me with the coefficients. What goes first? 3, -12, 3, 18. So don't just assume that the terms that are given to you are in the correct order, right? It has to be in standard order, standard form, which is descending order of degree. And you do need a placeholder for any term that's missing, including the constant, as we saw yesterday, yes? Has to be a 0 if there's no constant. Okay, and now, what are we going to put on the outside? A -1 or a positive 1? -1. We synthetically divide with the root. So here we go, -1. And then if we do it right, and or they were not lying to us about the x plus 1 being a factor, we should get a 0 here in the remainder box. All right, step 1, let gravity do its job, bring it on down, right? Then we multiply and add. Multiply, add. Multiply, add. So we get -3, -15, 15, 18, -18, and lo and behold, we get 0. Now here's something that I want you to be sure that you never ever do. If the numbers get a little bit uncomfortable, later on they might, don't get to this step here and just be like, well, I know it's going to be a root. It's got to be a root, so this has got to be then for sure right here a -18, right? Actually do the math and make sure it comes out to be the opposite of that number so that you do in fact get 0. Because if you just put the opposite of that number there, then these numbers down here could be wrong, which means as you proceed, it's going to be even wronger. And you don't want to do that. So actually do the math. All right, so those down here, the 3, -15, 18, that's the distilled product. Those are the coefficients of our depressed polynomial, which means it's now degree what? 2, right? So we factored out a linear factor from an x cubed. So these are the coefficients of your x squared. So all you have to do now is just add the variables back to it. 3x squared minus 15x plus 18 and set it equal to 0. So here we are. We're home free. We know how to solve quadratics. Let's see if we can factor it. Right now it's still kind of early, so maybe these still factor. Later on when they get more fun, maybe they don't factor. And then we got the quadratic formula, right? What's the first rule of factoring, though? Yeah, the greatest common factor, right? Which in this case is just 3. So you factor out the 3, and you get x squared minus 5x plus 6. And then keep the 3 there. This looks like it should factor. And it's either going to be the old 6-1 combo or the 2-3 combo. What you got here? Minus 3, minus 2. Good. Or minus 2, minus 3. Commutative property. Either way. There you go. Now, we need to make sure we answer the question. Did it want us to get the prime factorization, or did it want us to get the roots, or what? Let's see. Given that x plus 1 is a factor, find all the zeros. Okay. So I think we can list them now. So let's go ahead and write in a complete sentence. And you need some kind of transitional summary word. You can put therefore, thus, or my favorite, so, okay, kind of like Kermit the Frog there, the roots of, what's our function's name? H of x. So the roots of h of x are x equals, and let's go ahead and list the one we started with, -1, comma, 2, comma, 3. What about the 3 in the front? Is that a root? No, that's not a root. That's just a constant. So the roots are the x values that when you plug it into the two factors give you 0, one of which happens to be 3. Now, how do we know the search is over? How do we know that those are the only ones? Because there's 3, and we found 3, and that's all there is, right? Because the degree of the polynomial was what? 3, and we found 3. So what's the multiplicity on those? They're all M1s, right? If we have 3 distinct roots, then they all have to be M1s, because as we're going to learn soon enough in the next section, Carl Friedrich Gauss, Johann, proved the fundamental theorem of algebra, which basically says a polynomial degree n is going to have n complex zeros. And there they are. So let's see if we can sketch a graph. Actually, let's do something else first. Let's go ahead and write the prime factorization. But let's do it by the factor theorem. Let's do the factor theorem factorization, because I want to distinguish between the two types. Remember, the factor theorem says if x minus a is a factor, x equals a is a root. So that means that your linear factors have to have 1s in front of the x's. So we can start down here. We got 3 times something times something. So let's say h of x, it equals 3 times x minus 2, x minus 3, and then of course the other factor, since we synthetically divided with a -1, the other factor from that is x minus -1 or x plus 1. And there is your, that is not only the prime factorization in terms of linear factors, but it's also the factor theorem factorization. And what's the difference between the two? For the factor theorem, your coefficients of your linear factors of x have to be 1. Okay? They have to be a 1. So that when you see x minus 2, you know 2 is a root. X minus 3, 3 is a root. Okay? So 3 ends up being our a value from the previous section. Remember the a? It was your vertical dilation factor. But it also ends up being the leading coefficient. And if you look at it in an expanded form, it is the leading coefficient. So when you write it in the factor theorem form with coefficients of 1 on your x's, the number in front will always be your leading coefficient. All right, now let's go ahead and sketch the graph. We need a y-axis and we need an x-axis. Let's go ahead and pick a flavor. With which flavor should we graph? So many, right? Like you're at the snow cone stand. What do you call when you get a mixture of all of them? Suicide. They call that a suicide. That's kind of a pejorative term, though, right? We should come up with another name, like a grand festival mixture assortment. I don't know. Maybe that won't stick. I don't know. It's kind of long. I just picked burnt orange, pumpkin flavored. Pumpkin flavored. Today on campus, for the teachers, they're having pumpkin palooza. Whatever that is. Yeah. Apparently in the teachers' lounge, they're going to have all things pumpkin. Like pumpkin eggnog, pumpkin bread, pumpkin Twinkies I've seen. Pumpkin Pop-Tarts are excellent. Pumpkin sausage, pumpkin pizza, pumpkin hairdos, pumpkin rocks, all kinds of weird things. All right, so 2 is a root, 3 is a root, and -1 is a root. Okay, so we got the roots. They're all M1, so they're going to what? Cross, bounce, or wiggle? Cross. The right-hand behavior we said was positive infinity. We never said that on the recording. But because the leading coefficient is positive, that's the right-hand behavior. Because it's an odd degree polynomial, it comes in the bottom. So that's kind of important for sketching it. So it comes in the bottom, crosses at each of those, and exits the top. So remember, you're coming in kind of exaggerating the curvature. You don't need to go so high or so low. But if you do so, just be careful. You do want to exaggerate the fact that it's hugging you know, as it comes in or goes out. So it's going to be one of those right there, right? So don't have it like doing this, walking like an Egyptian. Exaggerate the curve as it goes out. Yeah, okay, good. And the higher you go when you cross the x-axis, the more difficult it is to kind of make it do that. Now, the y-axis is not drawn to scale. If you were to actually sketch this function on your calculator, the y values might be well above negative 10 and 10, which are what the standard viewing window is. So if you graphed it on your calculator, it would probably do this. You would just see like 3 vertical lines. Okay, so the but it would probably cross at the right place. Yeah. So your calculator actually does a much inferior job for sketching it than what we do. All right. In fact, we can figure out what the Y-intercept is. What's the Y-intercept? Go back to the expanded version. 18. Okay. So notice, is my graph drawn to scale on the y-axis, same as the x-axis? No, because I'm calling this right here the point 018, and on the x-axis I'm calling that 3. So now is it drawn to scale on the y-axis? Yeah, because I've labeled 1 point. Very good. So the scales on the x and y-axis do not have to be the same. I'd rather you drew a more meaningful graph like that, where you could see the local behavior, rather than drawing it to scale on the preserved x and y axis and having it just be tong, tong, tong. All right. Pumpkin Palooza. So today our graphs are even made out of pumpkin. See that? Mine is. Pumpkin spice. What's the difference between pumpkin and pumpkin spice? You got spice as pumpkin, right? Like spice, like what? Like garlic? Or jalapenos? Or dill. That's like the universal spice, right? Who doesn't like dill with anything? It's dill weed, though, right? It's a weed, and you get the dill from the dill weed, and you add the dill. Now, dill weed sounds like a really bad insult to someone, right? What's up, dill weed? Like, oh, thank you. I'm the weed that gives dill, the universal spice that goes with everything. Thank you for the compliment. Whatever, dill weed. All right. Nutmeg. Yeah, I'm lying about dill weed, right? We're on the same page with the joke about the dill. Yeah, nutmeg maybe is a little more appropriate, right? Yeah, but nutmeg doesn't sound like an insult, right? What's up, nutmeg? Yeah. Okay, that doesn't sound bad, though, right? That kind of sounds cool. Nutmeg. What's up, nutmeg? Number eight. Got to keep remembering that this is being recorded. This is going out there. All right, example 8. I didn't get much sleep last night because, the game went late, and then last time I looked at the clock before I went to bed, it was 3:30, and then I got up at 5, so I'm like doing like I did in college, functioning on coffee and math and a little bit of ramen. Okay, so example 8. We got this right here. It's a cubic polynomial once again. Here we're going to list all the distinct possible rational roots, and then we're going to find the remaining roots given that 3x plus 7 is a factor. Then we're going to sketch the graph. Okay, listing the possible rational roots, OMG, wow. It's going to be of the form P over Q, where P is a factor of what? Say it. I know it's big. 147. Gosh, dang it. Over Q, a factor of 9. Now, 147, someone last period optimistically said, that one's prime. And I'm like, I wish it was. But it's not. Yeah. It's divisible by 3 because its digital index is divisible by 3. What is the digital index of 147? 12. And what's the digital index of 12? 3. How do we do that? We just add all the digits together. 7 plus 1 is 8. 8 plus 4 is 12. And then if you get another 2-digit number, add those together. 1 plus 2 is 3. And if that number is divisible by 3, then so is this number. So 12 is divisible by 3, and so is 3. Its digital index. So the digital index of 147 is actually 3. It's a 1-digit number. But here's what. Again, if you don't tell the teacher, I won't. So let's just not and say we did. Okay? Let's just not and say we did. I think y'all have the idea down of listing the possible rational roots. Please tell me you do, or do we need to see it here? You don't want to do it? I don't. Okay, good. Yeah. But let's just skip that part. Now, back in the day, we didn't know 3x plus 7 was a factor, so listing the possible rational roots was actually a good thing for us because we had no idea what any of the roots were going to be, and that narrowed down the list, the candidate list of the possible decent solutions. And even if the list was long, like 25, 30, or it wouldn't be 25, right? It'd be an even number, 26 or 30, we would embrace that because trying out 30 things by synthetic division is a lot fewer than trying out infinitely many things, right? And it's not as if we had some place to go either, right, back in the olden days. Sorry if you lived back in the 18th century and you're listening to this. No offense. Well, if 3x plus 7 is a factor, what is the root that goes along with it? What kind of 7/3? Negative 7/3. Now, you got to be careful with a factor like this. It is linear, right? It's linear. So it's prime per se, but it's not in the factor theorem form. So you can do one of two things. You can either set that linear factor equal to 0 and then algebraically solve, right? Bring the 7 across, divide through, and you get negative 7/3. Or you can put it into factor theorem form, which means the coefficient of the x term has to be a 1. So you can factor a 3 out of both terms, and you get x plus 7/3. And now by the factor theorem, if x plus 7/3 is a factor, what is the corresponding root? Negative 7/3. Either way. So this would be the difference between just the general prime factorization, in which 3x plus 7 could be a factor, versus the factor theorem factorization, where it's always x plus or minus, and then the numbers out front become your leading coefficient. Okay, sweet. At any rate, we can synthetically divide out the root. So the coefficients are, in no particular order, no, you can't say that, in a very particular order, right? 9, 15, negative 77, and last and least in this case, it is the smallest of the coefficients, negative 147. No placeholders needed. You can kind of come back and double check. Go to your largest degree and just count down to 0. And make sure you got them all. 3, 2, 1, 0. You can count like that, right? It's kind of fun. 3, 2, 1, 0. Get lower each time. And when you do that, it kind of sounds like the beginning of a Paula Abdul song. Okay. No one knows Paula Abdul, anyone? Former Lakers dancer, had a bunch of hits in the 90s. All right. What are we going to synthetically divide with, guys? 7/3 or negative 7/3? Negative 7/3. You have to excuse me, all this craziness is just the ramen talking. Bring down the 9. Now, we are faced with the choice here of whether to multiply and then divide or divide and then multiply. And of course, it doesn't matter which way we do it, but you all now know about being efficient as well as effective. And so you all know now as a general strategy to go small before you go big, right? You've heard that before. So which one should we do? Multiply first or divide first? Divide. Good. What's 9 divided by 3? 3. And what's 3 times negative 7? Negative 21. Cool. And then you add and you get negative 6. And we'll divide again. Negative 6 divided by 3 is negative 2. Negative 2 times negative 7 is 14. And then when you add, you get negative 63. Negative 63 times 7. Oh, no, I'm not doing that. Negative 63 divided by 3 is negative 21. Now, negative times negative is positive, so what's 21 times 7? I hope 147. Do I just put 147 there and hope that it is? No. I actually do the multiplication, and I get 21 times 7 is, I hope 147. Yeah. No, it is. And you get 0. Okay. So now we're looking at the coefficients of a polynomial of degree 2, which means we've got it made, right? We are on second base. It's the 10th inning, and there's a slap shot hit down the third base line, and we're going to score from second, and we're going to win the World Series for the first time in 108 years. It's going to happen. We've got it. We've got it made. 9x squared minus 6x minus 63 equals 0. Now we try to solve that by factoring. What's the first rule of factoring? Common factor. What's common? 3. So that leaves us a 3x squared minus 2x minus 21, still equaling 0. And this is the fun type to factor, if it factors at all. Bless you. If not, we still have, bless you, the quadratic formula. Now, 3x squared, that's only going to factor one way because 3 is prime. So it's a 3x and an x. Now, 21 doesn't have many options either. It's either going to be a 1 and a 21, which is probably not going to be it because, bless you, our middle term has to be a 2, which is a relatively small number. So our factors have to be within 2 units of each other. So what are some other factors of 21? 42 and a half? No, we use integers. Good. 7 and 3? And so a 7 and 3, maybe a 3 would go there to couple up with the 3 to give us a 9, and maybe the 7 will go there. And because our middle term has to be negative, the larger product of 9 has to be negative. So that has to be positive. Yeah? Good. So now we have it factored. Now this is a prime factorization of that quadratic, but notice again, it is not in linear form, or the factor theorem form, because we still have a 3 there. But that should work. Now, answering the question, it says list all the distinct possible rational roots. So let's go ahead and list them. So the roots of, what's our function's name? Hector? No, f. Of f of x are x equals, let's go ahead and list the first one that we used up here. Don't forget him, right? He started us off, negative 7/3. And then we can list the other 2 that we get from our quadratic factorization. What's the root from the first factor? Negative 7/3. Again, do we have to list it twice? No, but if we're going to graph it, it would be good to know that it is a double root. So I'm going to go ahead and put an M2 by it. Now, if you don't put any M's by any of your roots, okay, if you're not sketching it, that's fine. But if you are sketching it, we're going to assume they're 1s. And once you put one of them as an M2 or an M3, then it's customary to kind of put it behind the others just for clarification. And the other root then would be 3, and of course it's a single root, so it's an M1. So now if we're trying to graph it at negative 7/3, the graph is going to what? Cross, bounce, or wiggle? Bounce. And at 3, it's going to what? Chirpy, chirp, 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 quack, 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 or is it going to waddle, waddle, waddle? Chirp. It's going to cross, right? It's going to cross. If it were at Worst Fest this Friday, it would be doing all 3 of them, right? When is the German club going to Worst Fest? Next week? Next Wednesday? Monday? Monday and Wednesday? All week long? Okay. Let's do 2 things here. Before we graph it, let's go ahead and write it in its prime factorization. Okay? So here we go. F of x is, now let's always start with the one we synthetically divided. Okay? Now notice I got the root negative 7/3 from that linear factor that did have the 3 there. But when I synthetically divide with a negative 7/3, I am claiming that what is the factor that goes along with it? X plus 7/3. And the 3 that I factored out over here to get that root, it's still contained inside this over here. So now when I come down here to the bottom and I have that factorization, that would be the other factor that I multiply over there. So now it's going to be times 3 times 3x plus 7 times x minus 3. Now, of course, that is not a pretty version of it at all. So let's do a couple things here. You could do one of 2 things. You can distribute this 3 inside that first factor, which would make it relatively pretty. It would make it a 3x plus 7 times the other 3x plus 7. You would have 3x plus 7 squared times x minus 3. That right there would be considered a prime factorization because you have linear factors. But it is not in the factor theorem form. So the other thing you could do from this step here is rather than distribute the 3, you could make the coefficient of the other 3x plus 7 factor a 1 by factoring out another 3. And that would give you a 3 times 3, which is what? 9. And then you would have an x plus 7/3 squared times x minus 3. And that would be another prime factorization that is in factor theorem form. Okay? Now that is the way maybe I prefer it, simply because now you could say, oh, if x plus 7/3 is a factor, then negative 7/3 is a root, and it's a double root. And 3 is a root because x minus 3 is a factor. And of course, now the number out front is what we were calling a. So that's your vertical dilation factor. Okay, and if you look at the beginning, it's also then the leading coefficient. So when you have your factors, linear factors with coefficients of 1 on the leading term, then the number out front will be your leading coefficient. Now, we do need to sketch it. It said to sketch it, and we haven't done that yet. So let's go ahead and do that. I'm going to cut this and move it over here where we have some real estate. Kind of move it. And now we need an x and y axis, so that's easy to build. There we go. And we'll throw the roots down. Negative 7/3 and 3. So I'll do 3 first because it's a little bit easier. There's 3. Now negative 7/3 falls between which two integers? Negative 2 and 3. So it's going to be about right there. And that's how I'm going to do it. I'm not going to like draw negative 2 and negative 3 and then put a line in between them. I'm just going to draw a line over there. That's reasonable compared to where I put the 3. I'm just going to label it as negative 7/3. Okay, so now we need to know a couple things before we complete the graph, right? What's the right end behavior? Positive infinity, because 9, the leading coefficient, is a positive number. And because it's an odd degree polynomial, the left end behavior is negative infinity. Okay, so that helps us out. We know it's coming in the bottom, it's going out the top. Now, when I get to the roots, I need to know what I'm going to do. Bounce, cross, or wiggle. At negative 7/3, I'm going to bounce, and then at 3, I'm going to just cross, yeah? So let's go ahead and pick a zany flavor for the graph. Tutti Frutti is always a good flavor. I don't know how they make that. Let's call that Tutti Frutti. So we'll come in here, and I'm going to bounce, cross at 3. So again, the higher up you go, the harder it is to kind of come back down and preserve that curve. So you'll get better at it with a steady hand. But there you go. And notice my bounce didn't quite match up perfectly, but that's okay. It's close enough. All right, any questions on number 8? Is it getting easier? Is it getting more fun or more boring? They're thinking. I know. It's hard. It's not cool to say math is fun, so I can see why y'all are reluctant to do that. Let's look at number 9. Find all the real zeros of that function. List all the distinct possible rational roots and use synthetic division to test your possible rational roots. Okay, this is a 4th degree polynomial. If our goal is to get it down to a quadratic at least, I need to know how many roots. 2. And on every problem we've worked so far, there have been some kind of clues or hints that have been given to us that have allowed us to do so. Do we have any such hints here? Did they give us a root or a factor? No, we need 2 of them. So guess what? Now we kind of have to do like they did in the olden days before calculators and computers. If they wanted to find the solutions to that polynomial, they really had to come up with the 2 on their own. And trial and error was really the only way to do it. But, of course, we have a way to narrow down the candidate list so that we're not trying values that had no shot at working. And that's the rational root theorem. So let's go ahead and list it here. These numbers are a little bit more manageable. So P over Q. This is what we did on the quiz yesterday. P is going to be a factor of what number? 8, yeah. Notice it is written in descending order, so don't take that for granted. 4, 3, 2, 1, 0. So 8 is the constant. So factors of 8 are plus or minus 1, plus or minus 8. List them as factor pairs. It's a lot easier. Then go up 1 from the smaller factor. 2. Does 2 go into 8? Yeah. Plus or minus 2, plus or minus 4. How about 3? Nah. How about 4? Got it. Now, once you get to half the number, the search is over. Okay? If you've already worked your way up from the bottom, as soon as you get to one of the factors that's half that number, you're done. All right, now 2 in the front is your leading coefficient, so it's plus or minus 1, plus or minus 2, and you're done. So let's list the possibilities. So the possible rational roots, the PRRs. This time, let's not write it down if it's a repeat. Instead of writing it down and then coming back and crossing them out, let's just think about it as we're writing it down. And if we've already got it, we don't need to write it again. Now, the first line is always going to be there because it's all of that over 1. So your factors of your constant are always possibilities. But now we have another factor of the leading coefficient. So now I'm going to put all of those over 2 and simplify in my head with y'all's help. So the first one, plus or minus 1/2. Do we have that one written yet? No, so I got to write it down, plus or minus 1/2. What about plus or minus 8/2? What's 8 divided by 2? 4. Do we have it? Yep, good. Plus or minus 2/2. That's known as 1. We already have it. Plus or minus 4/2 is 2. We already have it. So the only additional one that we picked up was plus or minus 1/2. Now here's a good question for the examination, which is now when? Tuesday. If you weren't here, I said yesterday the exam is postponed to Tuesday. How many possible distinct rational roots does this polynomial have? 1, 2, 3, 4, 5 positive, 5 negative, so 5 times 2 is 10. Good. 10. 10 would be the answer. That's a lot easier than having you list them out for a multiple choice question. All right, so what does that mean? That means that we only have 10 values to try out using synthetic division. Are any of them guaranteed to work? No. But at least if we try all 10 and none of them work, then we know that the solutions, if they're not rational, have to be what other 2 types? Irrational or imaginary. And that's what we're going to be studying going forward in the rest of this section tomorrow and on the next section. So let's write out the coefficients. We got a 2, a negative 7, a negative 8, a 14, and a positive 8. It's a fun word to say. Chad 8, 5. All right. Now we just need to do trial and error. Here's our candidate list right there. Let's see. Rodifer. Pick one of the 10 for us to try. There is no wrong answer. Negative 4. You were discerning for a brief moment there. It was an intense discernation. You were negative 4. So you seriously thought about it, and I respect that. I appreciate that. It wasn't just a random shot in the dark. Thank you for your consideration. All right, so negative 4. All right, we're going to try it out. So we bring down the 2, and we multiply, and we get negative 8. That gives you negative 15. That's going to give you positive 60. Minus 8 is positive 52. Times negative 4 is going to give you negative 208. Okay. You're still going with it? So minus 194, 184. $194. Positive 6, 7. Okay, so Rodifer, I'm going to go ahead and put a list of Rodifer's failures over here on the right. Okay? Oh, hang on. Rodifer, you did not fail. You know what? You successfully found a value that did not work. And so I like that. So we're going to put Rodifer's success stories over here. Okay? Successful wrong answers. Wrong, successful answer. It is trial and error. So we have one fewer number to try now. Yeah? So let's go ahead and clean the palette here, and we'll try it again. You said 1 again. You wanted to redeem yourself with a 1? I don't even know if 1 works. I don't know the solutions. We're just literally trying it together, right? 2, 2, negative 5, negative 5, negative 13, negative 13, 1, 1, 9, which is German for what? No. So, yeah, no, doesn't work. But you know what? 2 down. How many to go? 8 to go. Hey, Blake Fain's leaving. All right, let's let a girl pick one. Let's let a girl try. Uh-huh. Let's let a girl try. Bronco, pick one. Don't pick negative 4 or 9, but any other number will work. 4. 4. 4. I'm going to try 4. 4 is going to be the color of the girl's number. Okay, we had a boy try it twice. Now we're going to have a girl try it. See how the girls do. Bring down the 2, you get an 8, you get a 1, you get a 4, you get a negative 4, you get a negative 16, you get a negative 2, you get a negative 8, you get a 0. Way to go, girls! Yeah! Meow, meow. There you go. Way to go, girls. There you go, guys. You got to listen to the girls. Not today. It's like now the girls have taken ownership of the blue. They own it now. It's like when President Lincoln, after the Civil War, when Lee surrendered to Grant at Appomattox, guess what the first song President Lincoln had the Presidential Union Band play? Dixie. He had them play Dixie. And you know what he said? It was the South. Well, no, it was a favorite song of his, but he said, we beat the South. We own it now. It's ours. Let's play Dixie, which was the anthem of the South. So the girls own it now. The girls own blue. Lauren defeated Rutherford at Appomattox Row 3. Yeah. No, it's not a competition. I just chose blue because I like blue. I don't know. And it could have just been as easily as Lauren picking 2 wrong ones and Rutherford picking 1. It is just trial and error. Okay. So here's the good news. We have one that works. How many do we need, though, to get to a quadratic? We need 2. So we need 1 more. Do we have time to try 1 more? Sure. Now, here's the thing. When you try the next one, you don't want to come back up here to the top, because any root that is left in the original polynomial is still going to be a root of this polynomial. And what you can even do is redo your rational root theorem, because now you have to have a factor of negative 2 and 2 that work. So I don't think we're going to have time to try another one, but we'll pick up there tomorrow, and we're just going to continue the trial and error process on this one here. And maybe we'll go back to another guy to see if he can claim pink for the guys. Yes, sir, wheat. Yeah, the homework's not due tomorrow. It's going to be due on Monday. We'll be able to finish tomorrow. Oh, it is? Oh, okay. No problem. Well, you put what you could in there. Thank you, sir. I appreciate it. Yeah. Dill weed is actually an insult? It's like Urban Dictionary?
It says, a person is generally not smart, cannot realize the obviousness of what.
Oh, so someone's already grabbed that. Yeah. Interesting. Hey, have a great rest of the day, Twin Day, Mr. Corpy, and everyone else.
You gave me a mission for the quiz we took yesterday?
Holy cow. Did you take it?
Yes, sir.
And you turned it in?